Hi everyone, welcome. In this first video, we're just going to be tying up some loose ends, just doing a couple quick examples that we didn't quite have enough time for at the end of class last week. The first example or two I want to get to is covering half-life. So the half-life of a substance is the amount of time that it takes for a decaying substance to decay to half of its original amount. So here's an example. We have the half-life of carbon-14 is 5,730 years. So for example, a sample of 100 grams of carbon-14 will decay to 50 grams in 5,730 years. So my question for you is, which equation can we use to determine a formula for the amount left of a sample of A grams after T years? So I'll just let you pause and then unpause after you've given this problem enough thought and you're reasonably confident in your answer. So I'll assume that you've paused and unpaused the video at this point. And let's think about it. So let's say that the amount after T years is just going to be A times E to the KT, where A is like our original amount. And so after 5,730 years, we get A E to the K times, and this is like our T value, so 5,370. And after 5,370 years, that should take us to half of our original amount. So half of our original amount is just half of A, or 0.5A. So which of these does this match? Let's see. So we have 0.5A equals A times E to the 5,370K. So I think that it's matching D. Notice that, let's see, in B, this one almost works, but over here we have a T instead of a K, but like our T value should be 5,370, so this would be like, we would be solving for T when we're really trying to be solving for the K value, right? So our A is just whatever our initial amount is, and this K is just going to be like our decay rate. Okay, so yeah, the answer would be D. And then you could use that to solve for what K is. Well, let's actually go ahead and try to solve for that so that we can answer the following two questions. So let's say that we start with a 900 gram sample of carbon-14. What mass remains after 1,000 years? And then B, how long would it take a sample of carbon-14 to decay to 42% of its original mass? All right, so let's, to approach this problem, we need to first figure out what our formula is. So let's just say like f of t is going to represent the amount after t years. So that'll be A e to the kt. And let's try to find our k values. So we're using this formula here. So 0.5a equals a e to the 5,370k. We could divide both sides by a. So when you're doing like half-life or doubling time problems, like your initial amount like really does not matter for finding your k value. So anyway, we'll have 0.5 equals e to the 5,370k. So I can take natural log of both sides. And then my right side, natural log of e to the something is just going to equal that something. And then on the left side, we'll just have ln of a half. Oops, I forgot my k. And then I'll divide both sides by 5,370 to get my k value. So k is equal to ln of a half divided by 5,370. So over here, so this is going to be our k value. In part A, it tells us that our initial amount is going to be 900 grams. So that tells us that f of t is going to be 900 e to the kt. So I forgot it equals. So this would be ln of a half over 5,370 times t. So how much is going to remain after 1,000 years? We'll have whatever f of 1,000 is, which is 900 e to the, plugging in 1,000, ln of 0.5 times 1,000, all over 5,370. Just and then plug all that in, and then whatever your calculator tells you that this is equal to, that would be in grams. How much of that sample you have remaining? Okay. All right. Well, what about part B? How long would it take a sample of carbon-14 to decay to 42% of its original mass? So what I recommend doing here, just for like a knowledge check, is pausing the video and attempting this problem, or at least trying to set up the equation that you would try to solve to attempt that problem. Okay. So I'm just going to assume that you've had a chance to pause, and I'm just going to proceed, show you how to do it. But I do recommend pausing and trying this problem. How long would it take to decay to 42% of its original mass? So we want 900 e to the ln of a half over 5,370 t to equal 42% of its original mass, so 0.42 times 900. So we can proceed just by dividing both sides by 900, and then we get e to the, this is our k value, equals just 42%, or 0.42. We can again take ln of both sides. By the way, a lot of people like mistakenly say like multiply ln on both sides. You're not really multiplying by ln. You are what you're really doing is you're plugging these values into natural log. So you're really just taking ln of both sides. There's no like multiplication going on. Anyway, on the left side we have ln of e to the stuff, and so ln of e to the something is just that something. Remember our discussion about how natural log of x and e to the x are just inverses of each other. And then I can just multiply both sides by the reciprocal of ln of a half over 53.7 to solve for t. And so our t value will be 5,370 times ln of 0.42 divided by ln of 0.5. And that should be our answer. All right. We did a Newton's law of cooling problem. I want to do one more. Skip ahead. So just for a little extra practice. So a bottle of iced tea is being kept at 38 degrees Fahrenheit in a refrigerator. It is taken out of the refrigerator and placed in a room whose temperature is 73 degrees Fahrenheit. The tea warms to 50 degrees Fahrenheit after 30 minutes. Let's find a formula for the temperature of the tea at any time, where a little t is measured in hours. So T of t, capital T of little t, is going to be the temperature after t hours. All right. So let's go through the setup again. So Newton's law of cooling basically tells us that if an object has a different temperature than its surroundings, then the rate of temperature change is proportional to the difference in the temperature between the object and its surroundings. So I'll stay on that side. So what that's telling us is that the temperature the change in temperature with respect to time is proportional to the difference between the temperature and its surroundings. So we'll say like T sub 0 for like, or maybe T sub S makes more sense. T sub S for the temperature of the surroundings. Okay, so we've discussed things like dy dt equals k times y, and we intuitively said, well, if you have something like dy dt is equal to k times y, well, what's a function whose derivative is equal to just k times itself? Well, that function would be y equals e to the kt, because the derivative of e to the kt would just be e to the kt times the derivative of kt, which is just k, which is really just y times k, or ky. All right. But this derivative, or this equation, is not so different from this equation, because if you were to just say replace y with t minus t sub s, so this is just like a constant value, right? And so if you were to say, well, what is dy dt? Well, the derivative of y with respect to t is equal to the derivative of the right-hand side with respect to t. So we're doing like implicit differentiation here. So you get derivative of t with respect to t minus the derivative of the surrounding temperature with respect to time. But this is just a constant, right? So that would be like plus 0. The derivative of a constant is just 0. So these two derivatives are the same. So if I replace y with just t minus t sub s, I literally just go from this equation to this equation on the right, and this to this on the left. So these equations are really the same exact thing, okay? And I know I'm just like repeating myself from what we said in class on Thursday, but I just think that this concept is just a little difficult to grasp sometimes, and I think it's worth just kind of going through a second time. So anyway, the upshot of all of that is once we get that this is the solution to that, and this are really the same thing, then I can just go back here and then just replace y with this again and say T minus temperature of the surroundings is equal to e to the kt. So the temperature is equal to temperature of the surroundings plus e to the kt. And this is our general solution or formula for Newton's law of cooling. So back to this problem. So we have dt d little t is equal to k times t minus temperature of the surroundings. So, okay, it's taken out of the refrigerator, placed in a room whose temperature is 73. So 73 is the temperature of the room. So we want to use the temperature of the room here. The bottle of the iced tea is being kept at 38 degrees. So that's going to be like the initial temperature, but the temperature of the surroundings is going to be 73. So our formula is going to be T equals temperature of the surroundings, which is 73, plus A e to the kt. Did I have an A in the other slide? No, I forgot to have the, I always forget to put the A for some reason. Gosh. Okay. Anyway. So these all should have been A e to the kt. What I said like before was like true, but like the derivative of A e to the kt is also going to be equal to k times y. So this is like a more general solution to all of that. So my bad for forgetting that, but this would actually be our general solution. Ts plus A e to the kt. All right. Anyway, back to this. So now we just need to figure out what is our A and what is our K going to be so that we can have our formula for T. So it tells us that our initial temperature is 38 degrees. And it also tells us that the T warms to 50 degrees after 30 minutes. So T is being measured in hours. So 30 minutes, that's just going to be like half an hour. So T of 1/2 should be equal to 50 degrees. So these are the two bits of information that'll help us find these two unknowns in our formula. So the first one tells us that t of 0 equals 38, so capital T is 38. That equals 73 plus a e to the k times 0, so just e to the 0, which is 1. So we get 38 is equal to 73 plus a, and so a is equal to 38 minus 73. And what's that equal to? I think that's negative 35. Yeah, negative 35. So that's our a value. So t equals 73 minus 35 e to the kt. Now I'll use this information to solve for k. 50 is equal to 73 minus 35 e to the k times 1/2, so 1/2 k. Let's see, let's add 35 e to the 1/2 k to both sides. And let's subtract 50 from both sides. So we get 35 e to the 1/2 k is equal to 23. Dividing by 35, we get e to the 1/2 k is equal to 23 over 35. We can then take natural log of both sides. We get ln of e to the 1/2 k is just 1/2 k. That's equal to ln of 23 over 35. And so k is just going to be 2 times that. And so our formula is t of t equals 73 minus 35 e to the kt. So 2 ln of 23 over 35 t. And that would be our formula. All right, let's see. So we're doing this. Sure. Okay, this one, I think this problem is probably doable for you, so it's just a good practice problem. I'll let you try this, and then unpause the video, come back to it when you're ready, and then we'll go over it. So a sample of a certain radioactive isotope decays to 77% of its original mass in 8 hours. Find the half-life of this isotope, and then determine how long it would take a sample of this isotope to lose 60% of its original mass. So this is going to be another one of those just y equals a e to the kt problems, and we just need to figure out what a and k are. So actually, I don't think we even need to figure out what a is. We could just pretend that a is whatever we want, and then just kind of go with it. Or we could just never solve for k. Let's say this is like y of t. Okay. All right. So what is it telling us? So in 8 hours, it decays to 77% of its original mass. So 77% of its original mass would just be 0.77 times a. So we get a times e to the k times 8 is equal to 0.77 times a. And this would help us figure out what k is. So we divide through by a, and then we take natural log of both sides. We get 8k is equal to ln of 0.77. So k would be 1/8 of ln of 0.77. Okay. Well, how do I find the half-life then? So we really just need to solve for t in the equation. Y of t is equal to half of that original amount a. So a e to the kt equals 1/2 a. And k is 1/8 ln of 0.77. That's times t. And then we could, of course, get rid of that a. So e to the 1 over 8 ln of 0.77t is equal to a half. We take ln of both sides. We get 1 over 8 ln of 0.77 times t is equal to ln of a half. And then so t would be equal to 8 ln of a half divided by ln of 0.77. You could, of course, put that into a calculator. That would tell you like some number in hours, and that would be how long that it takes for the isotope to decay to half of its original mass. Part B, how long would it take a sample of this isotope to lose 60% of its original mass? This is going to be a pretty similar question. So here it's saying, when is y of t going to be equal to, well, let's think about this. It's going to lose 60% of its original mass. If it's going to lose 60%, how much are we going to be left with? We're going to be left with 40%, so 0.4 times a. So here we solve a e to the k t equals 0.4 times a. And then our steps are really going to be like almost exactly the same as we had up here, but instead of a 1/2 for all of these, oops, didn't mean to circle that. Instead of a 1/2 on the right-hand side, we're going to have just a 0.4 on the right-hand side. So I could literally just take this whole thing and just say, well, we're solving when does y of t equal 0.4 times a. Let's just make everything in black. 0.4, 0.4, 0.4, 0.4. And really all of these same exact steps just work out. When does y of t equal 0.4a? Well, this is what y of t is. You can divide through by a, take ln of both sides. Ln of e of something equals something. Then divide through to solve for t, and this is your t value. All right, cool. That's it for old stuff. And I'll see you in the next video for some new stuff.